Good, I will just start. Welcome to our presentation on legal norm retrieval with variations of the BERT model combined with TF IDF vectorization. My name is Sabine Wehnert, and together with my colleagues, we have also participated in the colleague competition. And our approach is for task 3 of the colleague competition, which is statutory law retrieval. So this task is about having a query that describes some situation or a statement simply, and you have to retrieve articles that are relevant with respect to that query. And this can be one or multiple articles. So the data set at hand that we used is the English version of the Japanese civil code, and we have fewer than 1,000 instances. And as I already mentioned, multiple articles can be relevant. So in the past 2 years, the best approaches were different. Sometimes it was a deep learning approach, sometimes it was a traditional machine learning approach. As we can see here that in 2020, the team LLNTU won with a BERT ensemble that comprised of 3 models. And then in 2019, the University of Alberta won with TF IDF and lemmatization, as well as stop-word filtering. So that was the reason for us to combine those 2 approaches and see if they could benefit from each other. And also, since we consider here retrieval also as a problem of not so many instances in this data set, in this case, we also were thinking about approaches to increase the number of instances and also enriching their content. We submitted 3 different runs, and the first run was our winning run. And this is here an overview picture of the workflow. So we used sentence BERT embeddings with TF IDF. And you can see here on this picture that we have queries and articles and that we pre-processed them with different methods. So you can see that we have 2 stages of TF IDF and then also sentence embedding. From that, we obtain the vectorized version of the article and the query, and then we compare those 2 with the cosine similarity after each pre-processing stage. And then finally, we compute the sum, normalize it, and then determine a threshold to have the final prediction whether this article is relevant to the given query or not. I would like to present you also some details on what we actually did. And the first thing I would like to present is the data enrichment. So consider Article 177 about acquisitions of, losses of, and changes in real rights on the movables, and so on. So this article is not that different from the other articles in the wording in the civil code. And we thought we could make it more unique by enriching it. So the first idea we had was to use the information that we could obtain from the civil code directly. So the civil code has some sections and headlines, and we just thought that we can take those as metadata and then simply parse them out. So you can see for this article 177, we could then get part 2, real rights, chapter 1, general provisions, and so on. And we simply took this text and appended it to the original article text and then further processed it using the tokenizer and the TF IDF vectorization. And here you can see that we also added some other crawled data from open source commentary that was originally in Japanese, but we translated it using the Google Translator API. And this open source commentary was then for this article 177. And for example, there were some concepts defined such as comprehensive succession. So this was also just appended to the original article text. The third enrichment we performed was to use the information from the task 4 that was on entailment that just Mr. Yoshioka has presented. And there we know that for this article, there are probably some queries that have a positive entailment label. And since we know that the entailment somehow indicates that the meaning is the same of this article and the query, if this is a positive label, we thought that we can also use it for document enrichment. And so we also appended all queries that have a positive entailment label to this article. That was the data enrichment. Now we talk about the 2-stage TF IDF. This is actually quite simple. So for both stages, we just used sublinear term frequency scaling and L2 normalization. And then the only difference between the two stages is basically how we enriched the articles. So stage 1 has the article with the metadata from the hierarchical structure of the civil code, and as well the article with the relevant queries from the entailment information. And stage 2 has only the metadata from the hierarchical structure. And at this point, you may wonder, well, why didn't you just take stage 1? And so we have made some comparison of just taking stage 1 and just taking stage 2. And there, usually the combination worked best. So on validation data, we saw much improvement. And on the test data of the collie competition, we just had almost no difference between stage 2 and then the combination. So combining this didn't harm and also could give a benefit. And then finally, I would like to show you some details about the sentence embeddings we took and the thresholding mechanism. So the sentence embeddings come from a BERT model that's called sentence BERT, and it has been proposed by Reimers et al. And here they have used the Siamese architecture that encodes the query and the articles separately, but then there's some parameter sharing between the weights that are then learned during the classifier training. And what we also used was a pre-trained model from those same authors that's called Paraphrase the Roberta base. And this model is particularly well suited, according to those authors, for natural language inference tasks. And since this retrieval task is also pretty hard, we thought that it could also benefit from such a model. And then the thresholding, for this, we have taken a kind of hard-coded approach that also was then simply saying, okay, for some index value, we have a specific similarity threshold, and then this article is included if it fulfills this condition. So with this run, we achieved the first rank in the collie competition with an F2 score of 72%. So precision and recall were quite high and balanced almost, and that's why we won in this case. There were other approaches that had a higher recall than we had, but well, F2 was then the measure that determined the winner here. And then let me just briefly also tell you about the other two runs that we submitted. One is a legal BERT with TF IDF. There we used the BERT model as a classifier for retrieval. And as a basis, we used the legal BERT-based uncased model. Well, and when you have a classifier for retrieval, you have the challenges of relevance class imbalance, because usually just a few documents are relevant and all the others in the corpus are irrelevant. And we also have the small data set. So this is quite a challenge for a deep learning approach. And what we did to make this a bit easier for our model was to decompose the data, in the sense that since we know that there are instances that have one query and multiple related articles, we decomposed them in pairs of one query and one article. So these were then sometimes multiple instances. And also we kept the original one where we had the articles still glued together as another instance in the data set. And what we also did was to decrease the number of irrelevant articles by just choosing the top 50 most similar non-relevant articles to a given article, because it's maybe more like it's harder for a model to determine why are those articles not relevant, although they are similar to a given relevant one. So that was our approach here. This is just the pipeline, the final one, where we have the TF IDF, cosine similarity, then max normalization, and then we perform the arithmetic mean between the values from the TF IDF and the legal BERT. From the legal BERT, we have the softmax for the relevant class, and then we have also some final thresholding. With this approach, we achieved an average position. So we were position 9 here, an F2 score of 67%. Well, and here you can also see recall was high and precision was a bit lower, so probably more advanced methods and thresholding would have helped here, and maybe this approach would be even also better than our first run. And then very shortly, the last run, that's the BERT score. So that was a pretty easy thing that we did, because it's based on an already available implementation. And what the BERT score does is that it simply computes the maximum pairwise cosine similarity between token embeddings that we obtain from a BERT model that is pre-trained. And so what you can see is that we have our training data, then we perform the BERT score computation, and we obtain an F1 score for the matching, and then we also just determine a threshold based on this F1 score. And here we were actually the last position, so we have the whole spectrum in the quali competition. And with this, we can also see directly, if you look at the values, that the precision is pretty low, and this is the reason why we were so bad, because recall is actually quite okay, but we probably have made a bad threshold decision or also overfitting in this case. So just to conclude, we found that pre-training and model architectures can play a vital role in using BERT for retrieval, and in our case, task adaptation and architecture, as we have seen in run 1, were better than domain adaptation in run 2. And also adding TF IDF to the model improved performance. And then further takeaways are that data augmentation, decomposition, and enrichment are useful. And we also found that BERT approaches require much tuning and experimentation. So if you try to recreate this from scratch, then you might not get the same results that we have, because there are random parts of the BERT model, and then learning can be very different if you start the process a second time. With this, I conclude my talk. These are some selected sources, and now I am ready to answer some questions.
Okay, thank you, Sabine. It was a really nice presentation and really interesting. So we have here one question. That is, one of your remarks was the benefits of incorporating external knowledge. In your opinion, what could be other structured external knowledge that could lead to an improvement in results or in explanation of its outputs? A rule-based knowledge could help on that in any way?
Yes, I think so. For example, we could try to find out how the query, like some characteristics of the query, if this query describes a particular situation, if there are person relationships, if we can maybe classify those persons as some kind of entity. So classification could help there, and also probably a rule-based one, just when some term is present. I think those rule-based approaches are very often also applied for the subsequent task of entailment detection, but probably for retrieval it would be also a viable choice. Yes, and regarding explainability, I mean, this is also a deep learning approach, so we are rather on the lower end of explainability. The only thing we could do is to check activation values or also analyze subpopulations of interest. So if we want to find out some parts of the data set, maybe particular hard queries, if we are good at those, or queries that then also describe particular cases compared to cases where we just have a query that almost has a direct overlap with article text. So we could try to also segment the data set and then find out where we are actually good at.